Welcome to Automated Flight Week 8, where we will continue a bit more on PID controllers. Now, we use a controller to change the behavior of a system so that its output has desirable behavior. Now, this is a typical setup of a simple system where we have a simple control system where we have the system we're interested in, which has a certain output and it has a certain control input, which we have here, which could be the acceleration of a car, the throttle of a plane, etc. Now, we have a desired reference value we want to achieve, a certain speed or altitude, and we want to make sure that the output of our system matches the reference value of that we selected. Well, if we take the output and the reference and we subtract them from each other, we have an error, the difference between the desired and the actual behavior. Now, to ensure that our system, which might not naturally exhibit the right behavior, does so, we can add a controller, and in this case a PID controller. I've added a sensor block here because let's say we're trying to achieve a certain speed in an aircraft. We don't directly measure the speed. We measure pressure. And so we have an air pressure sensor, we use a pitot tube and a static input to make sure that we can convert that pressure into a speed which then can be used to calculate that error. Now, in most situations we will not be dealing with this, but in practical situations you don't always measure the output you want to measure. It first goes through some other system like a sensor. There might be some filtering required because if we have a noisy input here, we might want to filter out the noise or at least attenuate it, and then it feeds back and creates an error. So for this lecture I will leave this part out so that we have in effect a unity gain feedback loop, and the controller is here. Well, what is a PID controller? Now, a PID controller consists of three parts: a proportional part, an integral part, and a derivative. And they all do different things with the input, well, the error into which is the input into the controller. So if we have an error signal, the proportional part simply multiplies it with a gain. The integral part integrates the error and multiplies it. So we have our the coefficient with which by which it is multiplied, which is called a gain. And we have our Ki, and then multiply that by 1 over S, which is the equivalent of integration, but then in the Laplace domain, or in the S domain. And we have a derivative part with Kd as its gain, and we multiply that by S. All these three things are summed, and we have our controller output. Now, as I've written it here, it is also a transfer function in the Laplace domain, just as this is a transfer function in the Laplace domain, and we can write out the whole thing, because if we sum these, we get Kp plus Ki over S plus Kd times S, and typically we write that as a single fraction where we divide the whole thing by S. Well, I'll just rewrite the whole thing. We get 1 over S Kp times S plus Ki plus Kd S squared, and that is now the transfer function of our PID controller. But why would we even want a PID controller? Well, we said before we have a goal of changing behavior, but what kind of behavioral parameters do we have? Well, we have, of our second order system, we have the natural frequency, the damping ratio, we have the rise time, the peak time, the settling time, and the maximum overshoot. And those are all behaviors we want to control with our PID controller. Now, we know that if we have a proportional gain, we can reduce the error between the reference and the output. But we can't get rid of it entirely, as we showed in the last video. The integral part, that makes sure that we can reduce that steady state error. And the derivative part will respond faster to larger changes in the error. But if we translate that to, well, let's take three rather prominent control parameters. What do these three things actually do? Well, proportional gain will decrease the rise time. An integral gain, increasing that, will decrease the rise time. And there are very few changes if we change the derivative gain. If we now look at the overshoot is the amount that it goes over our reference point before settling. We see that increasing the gain increases the overshoot, increasing the proportional gain and increasing the integral gain. Both increase the overshoot, and the derivative gain decreases the overshoot. And of course, we don't want a lot of overshoot, but we also don't want a very high rise time. And finally, there's a very small change in the settling time for Kp, and we have an increase in settling time if we increase our integral gain, and a decrease in settling time if we increase our derivative gain. But you can see already here that increasing the gain, well, there's no way of getting an optimal solution. You will always be trading off different values for our properties, our behavioral properties. So, well, let's next look at, so we have the transfer function for our system, we have the transfer function for our controller, but we have a closed loop system. What is our closed loop transfer function? Well, we've seen how to reduce block diagrams and how to calculate the transfer function of a system like that. And we find that it is CS times GS over 1 plus CS times GS. So now we have our PID controller. We know what CS is. So this is this transfer function. GS is our system. We know what the proportional integral and the derivative parts do to our behavioral properties. I think now it's time to look at at an example where we will use a PID controller, or at least parts of the PID controller, because you can also have a proportional controller, proportional integral and derivative. You can have any combination of these three parts. But let's first define our system and then see what we need. So let's take for our system GS is 1 over S minus 2. So this is a first order system. It is not very fancy, but the question is it stable? Well, to look at stability, we have to look at the poles in our complex plane. So here we have the real axis, here we have the imaginary axis, and the origin, and where does our, one pole lie? It lies at 2. Now, because this pole is in the right half plane, this system is not stable. It needs a controller for us to even, attempt to apply a reference and hope that the output will follow it. So we will try a PID controller. But we don't want to just try any PID controller. We have a specific desired behavior. We want not that our new pole is just in the left half plane. No, we want our poles at -1. So we want both poles to end up there. Well, let's first write out the closed loop transfer function of this particular system using a PID controller, which has this transfer function. So we'll apply this transfer function and this system and write this out. So what do we get? Well, Cs times Gs is 1 over S times S minus 2 times, and I'll just write it like this, KdS squared plus KPS plus Ki. That's the numerator. Now the denominator is 1 plus this. KdS squared plus KPS plus Ki times S over S minus 2. Now we will rewrite this 1 as S times S minus 2 over S times S minus 2. And I do that so that the fraction in the denominator and the fraction in the numerator have exactly the same denominator, and we can divide that and we get Kd S squared plus Kp S plus Ki over, well, this one, S squared minus 2S, but I can write that as Kd plus 1 times S squared, then S times minus 2S, I have a Kp times S here, plus Kp minus 2 times S plus Ki. So this is our closed loop transfer function. This closed loop transfer function should have all the poles at -1. Well, because it's a second order polynomial in the denominator, there will be 2 poles, both at -1, which means that we should be able to write this denominator as follows. And I will just, well, take this away, as we now have it, is that if we have 2 poles at -1, we should be able to write the denominator as S plus 1 times S plus 1, which is S squared plus 2S plus 1. So our denominator should equal this. Well, to ensure that we have a coefficient of 1 for the S squared, we need that Kd, Kd apparently is 0, so we have no derivative part. Kp minus 2 must equal 2, so Kp, our proportional gain, is equal to 4, and our Ki must equal 1. If we apply this PID controller, we will get the exact behavior that we want. So, and we can actually prove this by plugging in these numbers. And what do we get? Our closed loop transfer function is then equal, well, I'll just fill in these parts, is 4S squared, Kp 4S plus 1 over S squared plus 2S plus 1. So we have now the behavior we wanted. The poles are in the left half plane and specifically at -1, and which has stabilized our system. Now we could have chosen our poles anywhere. We could have said, well, we want to have a certain frequency, we want to have a certain damping ratio, and these will all yield values for Kd, Kp, and Ki. Now, is this the way we do it when we design a system? No, we will select our rise time and overshoot parameters in a tuning software, and out will come the desired values. So we can, so we won't be doing the arithmetic like we're doing now, but we'll use software to tune our parameters automatically based on some requirements for our parameters. So we've had a further look at a PID controller, discussed the effects of the different parts, the proportional part, the integral part, and the derivative part, and the effects it has on our behavioral properties. We've looked at the closed loop system for this particular configuration, taken an unstable system, and shown that we can actually choose the gain such that we have our poles in the desired location.